Okay, hello everybody. It's Tuesday, November the 10th. Don't have very many people. I guess it's too nice out and nobody wants to be inside. But anyways, we're going to continue with chapter 7, sampling methods. And before we go on, I want to know if anyone has any questions from chapter 7 that we've talked about already. Otherwise, we'll continue. Okay, no questions. All right. So the next part is the sampling distribution of the sample proportion. The same as a proportion that you've learned before. And remember, a proportion is just a fraction, okay, or a percentage. It's the same. So the sampling distribution of a population, the population proportion, gives you information about the population proportion, P. So for example, you might want to know the proportion of the population who use Facebook. Obviously, you cannot survey everyone on the planet, so you use a sample and get the sample proportion. Capital P, that's the bar. I was not able to put the bar there. It's the P bar, which is the sample proportion. Use that estimator for P. When studying the sampling distribution of the sample proportion, you also see a lowercase p bar. The lowercase version refers to a single value. Example, a single estimate. All right, I have a video on sampling distribution of the proportion, so let me get that set up. A little slow. And it's very slow. Okay.
Let's look into the sampling distribution of the sample proportion P hat. Here's a quick example. A random sample of 200 parts from a manufacturing process, 18 had major manufacturing defects. Here P hat, the sample proportion, is 18 out of 200, or 0.09. P hat represents the proportion of individuals or objects in the sample that have a certain characteristic.
Okay, I just want to make sure. Is there anybody that doesn't know what a proportion is? Everybody knows what a proportion is? Okay, as I mentioned, it's a fraction or a percentage. So in this case, it's 18. 18 had major manufacturing defects. It's 18 out of the sample out of 200.
In statistical inference scenarios, we use the sample proportion P hat to estimate the population proportion P. To develop the proper inference procedures, we need to know the characteristics of the sampling distribution of P hat, and that's what we're going to investigate in this video. I'm going to assume in this video that we are sampling from an infinite population, so that we are sampling only a small fraction of a large population. That is typically the case in practice. The situation changes a little bit if we are sampling a larger fraction of a finite population. We can view the sample proportion P hat as x over n, where x is a random variable that represents the number of individuals in the sample with the characteristic of interest, and n represents the total number of individuals in the sample. In many cases, x can be thought of as a binomial random variable with parameters n and p. So the sampling distribution of P hat is based on the binomial distribution.
Okay, first important point. Sampling distribution of a sample proportion is a binomial distribution. Okay.
Like the binomial random variable x, the sample proportion P hat is a discrete random variable. When we draw a sample, P hat will take on one of n plus 1 possible values. 0, 1 over n, 2 over n, up through 1. probabilities of these values will correspond to the probabilities that the binomial random variable x takes on the values 0, 1, 2, up through n. Recall that a binomial random variable x has a mean of n times p, has a variance of n times p times 1 minus p, and, due to the central limit theorem, is approximately normally distributed for large sample sizes.
Okay.
We're going to use these characteristics to derive the characteristics of the sampling distribution of p hat.
I just want you to remind you about these factors. They're the same because it's for a binomial random variable, x in this case for a sample proportion. It has a mean of n times p. It has a variance of np times 1 minus p, and is approximately a normally distributed curve for large sample sizes.
What is the mean of the sampling distribution of p hat? The mean or expectation of p hat is the expectation of x over n. Recall that when we multiply a random variable by a constant, the expectation gets multiplied by that constant. So we can take this 1 over n out front in front of the expectation. And we end up with this. And since the expectation of x is n times p, as we just saw, this is equal to 1 over n times np, which is simply equal to p. On average, the sample proportion equals the population proportion. And so we say that the sample proportion p hat is an unbiased estimator of the population proportion p.
Okay, just want to make sure everybody understands this formula. Okay. So you end up with 1 over n times np. The n's cancel out. You have 1 times p equals p.
What is the variance of the sampling distribution of p hat? The variance of p hat is equal to the variance of x over n. Recall that when we multiply a random variable by a constant, the variance gets multiplied by the square of that constant. So we can take 1 over n out front, but we need to square it. We end up with this. And we know the variance of x is n times p times 1 minus p. So the variance of p hat is equal to p times 1 minus p over n. The standard deviation of the sampling distribution of p hat is just the square root of that. The square root of p times 1 minus p over n. The sampling distribution of p hat is approximately normal if the sample size is large. This is, once again, the central limit theorem at work. But there is a bit of a complication. The sample size required to achieve approximate normality depends on the value of p. If p is close to 0.5, the sample size does not need to be very large. But if p is close to 0 or 1, a much larger sample size is required. So it's tough to give a simple, all-encompassing rule for when the normal approximation is reasonable. Here's the exact sampling distribution of p hat when n is 25 and p is 0.5. It's just the binomial distribution with a rescaled x-axis. Here, p hat can take on one of 26 possible values: 0, 1 over 25, 2 over 25, all the way up through 25 over 25, or...
Okay, so tell me, is this a normal distribution? Anybody? Does that look like a normal distribution? No one? Right, Roshani, it is. It is. Okay? Remember, if you see a distribution like this, right, you can just draw a line at the edges of the bars and see what kind of shape it makes. If it's close enough to a bell shape, then it approximates a normal distribution. So I want you to remember these things. These are the important concepts.
1. Probabilities are very close to 0 for values of p hat near 0 or 1, so they're a little hard to see in this plot. The sampling distribution of the sample proportion p hat is centered here at the value of p, 0.5. And when p is equal to 0.5, the distribution is perfectly symmetric. There will be some skewness when p is not 0.5. We can see that p hat has a discrete probability distribution. If we superimpose the normal curve with the appropriate mean and standard deviation, we can see that the normal distribution closely approximates it, even with a sample size of only 25. Now I'm going to increase the sample size and we'll see what happens. I'm going to leave the x-axis unchanged in these plots, but the scaling on the y-axis will change from plot to plot. So I'm going to take out the labeling on the y-axis. The normal curves that will be plotted all have an area of 1. Here's the sampling distribution of p hat for a sample size of 50, which looks a little more normal. For a sample size of 100, it looks more normal still. The superimposed normal curve seems to fit this distribution very closely. We didn't need all that large a sample size for the normal approximation to be reasonable when p is 0.5. But when p is closer to 0 or 1, there's going to be some skewness. A larger sample size will be needed for the normal approximation to be reasonable. Let's look at that. Here's the sampling distribution of p hat when n is 25 and p is 0.04. You can see that there is some right skewness. To make some features a little bit easier to see, I'm going to restrict the plot to values of the sample proportion between 0 and 0.2. Here's the plot for values of p hat between 0 and 0.2. And if we superimpose the appropriate normal curve, it doesn't fit the distribution all that closely. Increase the sample size.
Okay, just a quick. All right. Is this distribution skewed? And if it is, which side is it skewed to? Left or right? Left. So it is skewed. Does everybody agree? Right. What is it, John? Left or right? Okay. I don't want people to get confused by skewness. Remember, it's like you are looking at it from behind the graph as opposed to you're looking at it from the front of the graph. So it's behind, so it's skewed to the right. Okay? So just everybody get that. Pretend you're looking at the graph from behind the graph as opposed to looking at it from front the graph. All right? Okay, so it is skewed.
You will see that the distribution becomes more and more normal. Here's a sample size of 50, and here's a sample size of 100. If we superimpose a normal curve, it's looking a little more normal, but it's still not all that close. Here's a sample size of 200, and a sample size of 400, which looks a lot more normal. For a sample size of 800, it's looking more normal still. If we superimpose the appropriate normal curve, it fits the distribution quite well. So that's the situation when p is close to 0. For values of p close to 1, we see something very similar, just the mirror image of what we...
Okay, so the important point is, when p is close to 0, your sample size must be extremely large. Okay? In this one, we have an n of 800. Okay? The p-value is 0.04. All right? So if you understand that, does anybody not understand that? As p approaches 0, you must have a very large sample size. Does anybody not understand that? all right, great.
You see here. Let's take a very quick look at that. Here's the sampling distribution of p hat when n is 25 and p is 0.96. We see some left skewness and the distribution isn't very normal. But if we increase the sample size to 50 and then to 100, it's looking a little more normal, but we can still see some left skewness. If we increase the sample size to 200, it's looking more normal, 400, more normal still, and at 800, it's looking pretty darn normal. If we superimpose a normal curve, it fits pretty well. When p is close to 0.5, we don't need a very large sample size for the normal approximation to be reasonable. When p is close to 0 or 1, a larger sample size is required. That notion is summarized in the following rough guideline. Sampling distribution of p hat is approximately normal if n times p is at least 15, and n times 1 minus p is at least 15. There are other guidelines we could use, and some sources might recommend a number that is different from 15. This is a reasonable guideline. Overall, in summary, for large sample sizes, the sampling distribution of p hat is approximately normal, with a mean of p and a variance of p times 1 minus p over n. We will use these characteristics of the sampling distribution of the sample proportion p hat to construct appropriate confidence intervals and hypothesis tests for the population proportion p.
All right.
Let's look into the sampling distribution of this.
Sorry about that. Okay. And we'll go back to the slides. Okay, so just basically repeating what was in the video. The useful formulas for sampling distribution of the sample proportion, the expected value of the sampling distribution of p hat is the expectation of little p bar p hat equals p. The variance, as described in the video, is p times 1 minus p divided by n. The standard error of the sample proportion that's a square root sign. Square root of, enclose in brackets, p times 1 minus p divided by n. And remember, as the sample size increases, the standard error decreases, which is what you want. You don't want a large standard error. And then you can use the normal distribution if the following two formulas are true. NP is greater than or equal to 5, and n times 1 minus p is greater than or equal to 5. Now in the video, I use 15. My suggestion is if you can get 15, that's better. If you can't, okay. Greater than or equal to 5 is very close. And the z-score for the sample proportion, z equals capital P bar minus p divided by the standard error. So if we look at an example, a certain company's customers is made up of 43% of women and 57% of men. An aggressive marketing campaign results in an increase of women customers to 46%, according to a sample survey of 50 customers. If the company hadn't run the campaign, how likely is it that 46% of the customers would be women? Was the campaign worth it? Well, we don't have the amount of money that was spent on the campaign, so we can't distinguish that. We want to distinguish when it went from 43% up to 46%, was it worth that effort? So you're looking at for the probability that capital P bar is greater than or equal to 46%. So step one, Check that your sample size is large enough. N times P equals 50 times 0.43 equals 21.5. 50 times 1 minus 0.43 equals 28.5. Both are above 5, so you can use the normal distribution. They're setting 5 as the lower bar for normal distribution. In the video, they set 15 as the lower bar for the normal distribution. You can use whichever number you'd like to use, 5 or 15, it's your choice. So step 2, we want to find the standard error, the square root of p times 1 minus p divided by n. So we have the square root of 0.43 times 1 minus 0.43 divided by 50 equals 0.07. So from your understanding of a standard error, is that a large standard error or a small standard error? If you convert the 0.07 to a percentage, what do you get? I believe anybody can figure that one out, 7%. Okay, so is 7% considered a large error or a small error or an in-between error? Okay, now remember, and I'm going to bring this up a lot, and that was my error. We don't want to use adjectives of magnitude. In this case, yes, the error, when you have your error term as close to 0.05 as possible, that's a good approximation. Because anything within 5% error is considered, that's okay. 7% is not much more than 5%. So it's reasonable to use, you know. And if you want to use a rule of thumb, anything 10% or above, that's too much of a sampling error. Yes, 10% is large here. It is a large error. That means you either better increase your sample size, or as part of your design, there's something wrong with the design. You do not want something with a 10% error. Okay? Because if you get any statistical results that are significant, it may be a false positive. You have to elaborate. What do you mean? Why people are so happy about vaccines, though? What are you asking? Okay, Amir, are you saying there's a 10% error based on this? You're talking about this Pfizer vaccine that they talked about yesterday? Is that what you're talking about? Okay. You have to learn how to elaborate, Amir. Statistics, the more you say, the better it is. Okay? Remember, with this vaccine, they are at 90%, which means, would you want to take the vaccine? Because there's a 10% error there. Is there anybody in the class that would want the vaccine as it now, or you want to wait until that sampling error decreases? Anybody want to take the vaccine? Okay, and why are you going to wait? It's a perfect example for what we're talking about here. It's 2 people, there's 12 people or 11 people in the class. What do the other people say? They want the vaccine now, or you want to wait till the vaccine is at a better error rate? Song says wait. Roshani says wait. What about Samar? Siddharatha, song. Noah, John, what do you say? Wait. Okay, wait. Okay, so this is a practical, actually a very good example of looking at sampling error. As they get closer to 5%, which you don't know. We don't know, we don't have the data, we don't know how many trials they've used, and say they're at 7%. So what does that mean, Noah? When you say there could be unintended side effects, what does that mean? Can you elaborate on that? Noah, can you say something? You're saying if the vaccine is taken now, November the 10th, 2020, there can be defects. Is that correct? Is that what you're saying? You can speak if you want. That's easier. Or respond. Yes. Okay. And when you look at something, and this is good, this is really good. When you see a sampling error, and it's important when somebody is running anything, any kind of analysis, it's really important to look at that sampling error. Because you want that sampling error as close to zero as possible, because then you know that whatever is being said or whatever is being tested is fully functional. In this case, if we said that the vaccine, and we've been told by Pfizer that's at 10%. So you're not going to have, well, unless somebody's really silly, not going to take the vaccine. Because yes, you do not know what the side effects are. Yes, that's because the sampling error is at 10%. So I want you to understand how you can integrate that information. It makes you understand what the company, what an individual, what a researcher is trying to tell you. So are there any questions about that? About that sample error? I think this is really great. So it's a real example that you can use. So at this particular time, nobody should be taking, well, the company is not giving the vaccine to anybody. All right, let's go to the next slide. All right. So step 3, you find the Z score using the standard error you calculated in step 2. And Z equals capital P bar minus P divided by the standard error. You get 0.46 minus 0.43 divided by 0.07 equals 0.43. The next step is you look 0.43 in the Z table. The probability is 0.3336 or 33.36%. At the probability of 33.36%, it's fairly likely that the proportion of the women would have been 46% without a campaign. It's unlikely that the marketing campaign made a difference. Okay? How is this calculated? Sampling distribution of the sample proportion, value of 0.1664 in the Z table. And this is the area between the mean and Z. And that's where you get 33.36%. Okay, any questions about this? No questions? Okay, good. We finished chapter 7, which means the test will be on Friday and available from 5 o'clock, 5 p.m. on Friday until Monday at 5 p.m. Okay. Now, I just want to mention a couple of things that I guess I didn't elaborate on your test and your evaluations and your homework. Is that when you get a question, you know, that says, for example, in here, oops, here's the question, a certain company's customer, was the campaign worth it? That's the last question. A lot of people are giving their answers, and that's fine. And then I'm marking that as correct. What I want you to get in the habit of doing is answering the question in a sentence. Okay? You came up with a solution, a numerical answer. Okay? So in this case, so at the probability of 33.36%, it's fairly likely that the proportion of women would have been 46% without a campaign. It's unlikely that the marketing campaign made much of a difference. Okay? This is an answer to the actual question. So when you have a problem, and those are basically open-ended questions in the test, okay, I want you to write a summary statement of whatever it's asking. If it's not asking, that's fine, you just put the number down. But if it's asking, I want you to put the resolution in a sentence. Okay, because I'm not going to give you full marks if you only have the number, because that's not, if somebody, you're working at a company and somebody gives you a problem to resolve, you're going to want it in written form. They don't really care about the number. The number is part of the resolution, solution, sentence. So it's part of that, because there's a question that's being asked. Is that clear? Okay, so I want you to get in the habit, when you have an open-ended question, to answer in a sentence. No questions about that? All right, so a couple of other things, and that's my responsibility because I didn't say anything or I didn't say it fully. If your answer is in decimal form, like, 0.34, whatever, I want you to use 4 decimals, okay? And everybody's familiar with rounding the decimal, so you're going to be rounding or leaving the 4th decimal based on the 5th decimal. Okay, so is that clear? I'm gonna send this out in an announcement, but I want those people that are here today to understand that. So to answer as a decimal, it's got to be 4 decimal points. Okay, either rounded or not rounded. When you're using a percentage, and some people are doing this, I'm not sure why, you must have 2 decimal points, and you must round it off. You must round off the 2nd decimal point if you have to round it off. Okay? And the last thing is, some people, and I know there's a time frame in the test and there may not be enough time. This one is probably, you don't have to do it, but it would be good for me to see it, just to show your work on how you got the solution. A lot of people are doing that, and that's great. Some people are just giving me a solution. The problem with that is, what if you're a couple of decimal points off? If I don't see your work, I don't know how you got that answer. If I can see the answer, it may be something mechanical, it may be the calculator, whatever, it's only a minor error. But if you just give me a number, and it is not even the correct number, because I don't know what you did, whether you rounded it off incorrectly or you didn't, I can't give you the full marks. Okay? So, are there any questions about that? I'm going to send out an announcement about that. So I'd like you to do that for S7 and 8 and the final exam and the research paper and your homework. If you can do that, that's great. Any questions about this? No questions? Okay, so we finished chapter 7. And as I said, chapter 7 test will be on Friday, and I will give you the homework for chapter 7. All right. So we're going to start chapter 8, estimation and confidence intervals, the last chapter of this course. Of course, if you want to take the next course, that would be fine. Okay, so estimation and confidence intervals. We talked about this a little bit in the preceding chapters. This chapter is strictly about estimation and confidence intervals. So we'll just see a video on that. If it's going to, there we go. Okay.
Let's take a look at an introduction to confidence intervals, an extremely important concept in statistical inference. Confidence intervals are based on sample data and give a range of plausible values for a parameter. For example, we may be 95% confident that the population mean mu lies in the interval minus 0.2 to 3.1. In which case, the interval minus 0.2 to 3.1 would be a 95% confidence interval for mu. Or we may be 99% confident that the population standard deviation sigma lies in the interval 2.5 to 13.4. In which case, 2.5 to 13.4 would be a 99% confidence interval for sigma. An important point is that we construct confidence intervals for parameters. And so the interpretation of a confidence interval always relate to a parameter. Your mu is a population mean, a parameter. Your sigma is population standard deviation.
Okay, so remember, a parameter is referring to the population, not the sample. Okay, that's important.
Parameter. We never construct confidence intervals for statistics, so we will never have a confidence interval for x bar, say. That is simply not how it works. We construct confidence intervals for parameters. We may use a statistic to help us get a confidence interval. We do not construct confidence intervals for statistics. Confidence intervals always relate to parameters. Associated with the confidence interval is a confidence level, here being 95% and here being 99%. This means we can be 95% confident that the parameter mu actually lies in this interval. We'll see as we work through the methods in greater detail that we can pick this confidence level to be anything we would like. I could have picked this to be a 99% interval, say, but the result of that would have been a wider interval. So there's a trade-off between the confidence level we pick and the width of the interval. And for most purposes, we feel that a 95% confidence level is a reasonable choice. So 95% is by far the most common choice of confidence level.
Okay, sorry, I have a question. At 95% confidence level, what is your expected standard error? You have a 95% confidence level. What's the expected error? 5%. Amir, it's 5%, not 5. 5%. Get in the habit of doing that. Okay? Does everybody understand why it's 5%? Think about this is like a tolerance level. Okay? If you set your confidence level at 95% and your standard error is 6%, accepting the results. Would you accept the results if your standard error was 6% or 0.06? Why not, John? It exceeds 5% because you are the person that's setting the tolerance level. You set it at 95, that's your confidence level. Your standard error was 6%. You should not accept the results even though they may be statistically significant. All right? So, when you see, or if you've participated in any kind of surveys and they go, oh, 95 out of 100 people, blah, 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 they're setting at a 95% confidence level. We never hear what the standard error was. I'm not sure why, but they don't do it. Now, what's the problem with setting the confidence level at 99%? Is there a problem with that? What won't happen? You have to be more explicit, John. You have to explain why it won't happen. This is statistics. I've been telling everybody you have to explain what the result, why will not be possible. You've got a 99% confidence level. Can anybody help John here? Okay, but you're not telling me what that means. I set my confidence interval at 99%. What's the error that I'm expecting? You're not answering the question. What's the error that I'm expecting? It's at a 99% confidence level. 1% error, correct, Brenda. And a 1% error, what does that mean about what you're testing? What does that mean? If you get statistical significance at 99%, what does that mean about whatever you're testing? Nobody? Okay, if I set the level at 99% confidence interval and I get a standard error of 1% or less, then what can I say about whatever I did, whatever analysis I did? No, it's not that the 1% did not apply in the sample. Okay? Is that tiny? Is that relatively small? Is that relatively large? What is that? It's tiny, which means you're 99% confident whatever you were testing works on 99%. It can work on 99% of your population. So, if we go back to the example of the Pfizer vaccine, and they come back in 6 months or whatever time frame, and they go, we have a 99% confidence interval that the vaccine works. Are you going to take it then? Yes. Everybody else, what do you say? Only Amir is going to take it? Nobody else will? Roshani, are you going to take the vaccine if it's at 99% confidence interval? No, Roshani won't take it. Okay, probably. Okay, what? All right, right. Yeah, song, good. Okay, Roshani, why wouldn't you take it when there's 99% confidence? I'm just curious. Why would you say that, Roshani? You have an answer. If you want to use your microphone, that's fine. But this is a very important concept in statistics. Okay. And what does that mean, Brenda? When are you going to be totally happy to take the vaccine at 99%? Are you the same, Rashani? Guess what? You can never get, and this is something that you're going to pursue this, or you will never get 100% confidence interval. Never. Because you can never say you're 100% confident that whatever you're going to do is going to be 100%. There's always a 1% chance. And this is the level, and I'm not saying this is going to happen. I'm just saying the advisor sets their confidence interval at 99%. Okay, there will always be a 1% chance that it will not work. And what they're talking about is their first release would be 50 million doses, and you're supposed to take a double dose. So that would be 25 million people. What is 1% of 25 million people? Anybody? Anybody got a calculator? 1% of 25 million people. Somebody must have a calculator. 250,000. Okay? 250,000. That means, it doesn't mean for sure, because we're talking about, they're setting at a 1% error level. There's a possibility, there's always a possibility, that 250,000 people out of 25 million people, the vaccine will not work. Doesn't mean you get the virus. It means the vaccine may not work. Okay? Does anybody not understand this? Okay? It's very important to understand this concept when you're setting confidence intervals at 95 and 99%. Very, very, very few, whatever companies are doing things, the confidence intervals at 99. Why? Can anybody think of why a company will not do an analysis that says we're doing this at a 99% confidence interval? Can someone think of a reason why they don't set it at 99? Anyone? Can you elaborate, Siddhartha? What do you mean too many legal complications? Typing? I don't know what that means.
I'll just use the mic. Sorry, I was saying that I was still typing, so I
Yeah.
didn't. Yeah. So I said that there are too many legal complications in the sense that if they say it's 99%, they're taking too much of a risk because, like you said earlier, companies never give out 100%. Like
Nobody ever gives 100.
100% is unrealistic. So if they say
Correct.
99% is also a bit unrealistic for them to say 99% because when the data is collected and there's more than 1%, they could fall into like, if more than their predicted 1% gets COVID and it's like maybe like 20% and their chance, their rate's actually 80% effective, their drug's actually 80% effective, then it would cause legal implications for them.
No,
That's what.
okay, that's true. Okay, that can happen
Yeah,
because if it's at 1%, that's your error met. That's your error. You're saying that it's effective for 99% of the people who will get the vaccine.
yeah,
1%, it's a chance. It doesn't say you won't get, or the vaccine will not be effective. It says there's a 1% chance it will not be effective. And as you pointed out, so the first batch is supposed to be, and nobody knows who's getting this or where it's going to go. 25 million people will get the vaccine. There is a chance that 250,000 people, the vaccine won't do anything. Won't. And if somebody in that 1% gets the COVID virus, okay, they're within the 1%. But if, as you said, you have 250,000 and one person gets the virus, that company is going to get sued really bad. And that's why hardly you know, this is very serious. This is a virus. Something else, you might have 99%, but rarely does a company go out on a limb and say, well, 99% confidence level, we're going to say, this works or this doesn't, whatever. Okay?
so I actually take a medication from Pfizer, from the same
Yeah,
company, and
right,
it's a study medication. Um, it's nothing to do with COVID. It's just a study medication for something else. But when I
right.
was taking it, they were explaining to me like how they do their trials and
Yeah,
how they give out their percentages. So they explained to me like how you did just now, that they'll never give you like, I said, is this like, are there any side effects, or like will it work on me? And is there like a percentage? She said we try not to give out a percentage unless absolutely necessary. And
uh-huh,
what we do as well, we always cut it down a little bit. Like for example, if it's 95% effective, we'll say it's 90% effective, or
uh-huh.
like
Okay.
93, just to keep like a window of leeway for themselves.
Right, right. They want to protect themselves,
Yeah,
obviously.
exactly.
Okay, so just as another example, I got a flu shot. Okay, I don't know how many people in the class get flu shots, but on the whole, and again, the companies that produce the vaccine for the flu shot, they'll never say it's 100% because, of course, they're going to get sued. So just remember that when you're either participating in a survey or you're going to design a survey, um, usually people say 95% or 90%. They don't want to say 99%. Okay? So is there any questions about that? That's also extremely important. Any questions? No? Okay, we'll continue with the video.
Let's look at an example of something that appears in the media very frequently. Polling organizations often conduct polls investigating the public opinion of how the president is doing his job. These different organizations publish presidential approval rating. Suppose in a telephone poll of 1,000 adult Americans, 430 said they approve of the way the president is handling his job. These 1,000 people represent our sample. And in our sample, 430 said they approve. So we're going to call P hat the sample proportion. P hat is the sample proportion, and that is simply the proportion of people who say they approve. So 430 over 1,000, which is 0.43. The sample proportion P hat estimates the population proportion P. P is a parameter, and its value is unknown. And the sample proportion is a value we get from our sample. And so in our case, that was worked out to 0.43. Here, the parameter P is the proportion of all adult Americans who would say they approve if contacted by the pollsters in this manner. It is an unknown quantity, and we are trying to estimate it. An important question for us is how close is the statistic P hat likely to be to the parameter P? The sample proportion P hat, 0.43, estimates the population proportion P. P is an unknown quantity. Is it still conceivable that P is 0.92 or 0.04 or 0.56? what are the likely values of P? We're not going to be able to say with certainty how close P hat is to P, because P is an unknown quantity to us. But we would like some way of expressing how close we feel this P hat value is to the true value of P. And the way we choose to do so very frequently is through a confidence interval. We often express our uncertainty in the true value of the parameter with a statement like, the pole is believed to be accurate to within 0.03 19 times out of 20. First note that 19 out of 20 is simply 0.95 here. And so that's the same as a 95% confidence.
Okay, that's important because that's exactly what it is. All right. So when you see that in a polling example, 19 times out of 20, it's just at the 95% confidence interval, period. Okay, nothing complicated.
Level. What we're saying is when we're about to draw a random sample from the population of this size, that we are 95% confident that the sample proportion P hat is going to lie within 0.03 of the true value of P. This 0.03 is sometimes called the margin of error. And so P hat plus and minus 0.03 is going to be a 95% confidence interval for P. And in our case, that's going to be 0.43 plus and minus 0.03, or in other words, if we carry out the addition and subtraction, 0.40, 0.46. And this is a 95% confidence interval for the parameter P. And we can be 95% confident that the true value of the parameter P lies somewhere in the...
Okay, does everybody understand how he got 0.40 and 0.46? Any questions about how that came about? This is your confidence interval, 19 over 20 or 95%. Okay, this is your sorry, not your confidence, sorry. This is 95% confidence. This is the confidence interval. Okay, because it's 0.043 that was expressed in the previous slide. So it's plus minus because you want to go above and below whatever you're saying it is. You get 0.40 and 0.46. No questions about that? All right.
This interval. And as we work through the concepts in a little bit greater detail, we're going to learn why we can say within 0.03 and 0.95. Many statistics have sampling distributions that are approximately normal. In large part, this is due to the central limit theorem. In these cases, the interval will be of the form point estimate plus and minus margin of error. And we're going to use mathematical arguments to come up with the appropriate margin of error in these different situations. Not all confidence intervals are in this manner. In the problem, there will be two main issues. We need an appropriate method to construct the confidence interval, and then we will need to properly interpret the resulting interval. Properly interpreting a confidence interval is very important in statistics, and there are some subtle issues associated with that. So I'll look at that in greater detail a little later on.
Okay. Just want to mention.
Let's take a look at an introduction to confidence intervals.
Sorry. Who's ever coughing, can you just turn your mic off? Unless you want to talk. Thank you. Because everybody can hear your coughing. And I'm just going to go back to the PowerPoint. Okay, so I have a question. And I don't know if people were paying attention or listening or watching about the American election. And there was a comment about, oh, all the polling was off. Okay. Yeah, John? Why is it a fraud? Tell me why it's a fraud. Can you explain? Don't make statements without any valid information. That's what stats is about. Do you know why? Can anyone figure out why the polling was not an accurate reflection? It's a claim, John. That's not valid. That's not information. So, exactly. Here's my question. Forget about whatever Trump is saying or whatever. Why was the polling off? Can you figure out from what you know about the election? And remember what polling is about. Can anyone think of why the polling was off in their predictions? Nope, that is not the reason. Okay. Did everybody vote the same way in this election? Okay. How do you interview somebody who's sending in a mail-in ballot? Can you interview them? Right, Brenda? No. How do you interview somebody who sent it? You don't even know who sent in a mail-in ballot. And I don't remember what the number was according to how many mail-in ballots there were. So if you take those people, because usually when they do a poll, when they do a poll, they usually like interview somebody before they go and vote, or they interview somebody when they come out after they vote. With a mail-in ballot, you can't interview anybody. So I don't know, does anybody know what the rough number was for people who mailed in ballots? I'm thinking it was, that has nothing to do with this. He can claim whatever he wants. Until it's validated, it doesn't mean anything. It means he has an opinion and you have an opinion. Remember, stats is about data, real data, not made up data. Okay. So if you take out 50 million, whatever the number, let's say it's 50 million people voted by mail, you can't poll those people, correct? We're talking, this is across all 50 states where everybody is allowed to use mail-in ballots. So your polls are going to be inaccurate because it doesn't have a representation from those mail-in ballots. So the polling companies are making an assumption that the people who sent in ballots via mail are the same kind of people who went to the polling station and voted. Can everybody see how that can change what the polling will do? Can anybody not see that? Does everybody understand that? Does anybody not understand that? Okay, is everybody still with me? All right, I'm not sure. Okay. All right. Good. Well, at least Brenda, Song, yeah. Amir, great. Okay. Brissa, Wellington, good. Okay. You see how these things can change. Anyways, for this chapter, the learning objectives are defining a point estimate, defining a level of confidence, constructing confidence interval for the population mean when the population standard deviation is known, constructing a confidence interval for a population mean when the population standard deviation is unknown, constructing a confidence interval for a population proportion, and determining the sample size for attribute and variable sampling. Okay, so why do we use sampling? Well, we talked about it previously in chapter 7. To contact the entire population is too time consuming. However, I guess if everybody could access a computer, and not familiar with libraries, how many computers they have, but technically you certainly could get close to the entire population if they all had access to a computer. The cost of studying all the items in a population is often too expensive, although I would think that cost is going down, not that everybody's going to sample the whole population. The sample results are usually adequate, and they're adequate because as we increase our sample size, it approximates the normal population. And as previously said, certain tests are destructive, and checking all the items is physically impossible, but with computing, it now becomes possible. Okay, so a point estimate is a single value. It's 1 point derived from a sample and used to estimate a population value. Okay, single point. That could be the mean. That can be the variance. That can be the standard deviation, whatever. It's 1 point from a sample used to estimate a population value. And we can use that because why can we use that point? Somebody, why can we use a single point value to estimate population value? So I'm taking the mean of a sample and I say, okay, that's the mean of the population. So why can I say that? Anybody? Nobody? Okay. What have we been talking about? The larger our sample size, the closer it approximates the normal distribution, which is the population distribution. There's some point that changes the sample. I'm not sure what you mean. What does that mean, Amir? What are you trying to say? Ah, okay. Right. So, well, what's another point? If we have that, what can we use instead of the mean? The median, exactly. Remember, we're taking this from a sample. You think the mean is skewed? Well, we know the median is half on one side and half on the other side. So it eliminates the fact that maybe you have too many wealthy people or too many poor people. Okay, it's still a measure. It's still a single point. We can approximate the population from that. Does everybody understand that? That's very important. Okay, back to the slide. A confidence interval estimate is a range of values constructed from sample data so that the population parameter is likely to occur within that range of specified probability. Specified probability is called the level of confidence. So just in that example that we saw in the previous video about the confidence level being at 95% or 99% or 90%, that will give you the range of values because you cannot get the whole population. But if you have a range, you'll say 95%. You're confident that they will lie within, and that example was 3% of, whatever the mean was, or 2%. All right. And so what are the factors that determine the width of a confidence interval? Sample size, obviously. The variability in the population, usually sigma estimated by S. Okay, the standard deviation estimated by the variance. Desired level of confidence. So if you're doing, you're doing your case study, are you happy with 95%? Are you happy with 90%? What is the desired level of confidence, or what is the minimum desired level of confidence that you would be happy with? No one wants to talk. Okay, don't worry if it's not correct. Okay, Amir, you're happy with 95. Remember, think of it as when you're deciding on your desired level of confidence, you're saying what my standard error is going to be. If you're happy with 99, your standard error is going to be 1%. It's really, really strict. You're happy with 95%? That's 5% standard error. Now, we haven't talked about this, but what if you say, I'm happy with 90% confidence interval? What's the problem there? Yeah, so there's a 10% error. So what? What's that mean? What happens if you have a 90% confidence interval? Level. Yes, you have a 10% error. So what does that mean? Why is it too high, Song? I want everybody to start thinking about statistics. You're thinking statistically. So what is the problem with having a 10% error level? Could not apply in the sample size that we're looking for? Okay, you have to be more explicit, Amir. You have to describe exactly what you're trying to say. When you say that, I don't understand it. I'm not sure other people in the class understand it. What does that mean? You can use your microphone if you want. No? You're not sure? Okay. So 10% error would not be that much of a deal. Why not, John? Tell me why. You're not sure. Okay. And John, why is it 10% not much of a deal? John, you want to say something? Or you want to respond? Okay, does that mean you're ready to take the COVID vaccine from Pfizer? It's a 10% error. Are you ready to take it? Why not? It's only 10%. It's not much of a deal, is it? John? You said 10% is not much of a deal. So I asked you if you want to take the vaccine. You said no. Tell me why you don't want to take it now. You want to use your mic? Can you respond? John, do you hear me? Well, then why is it not much of a deal? You just said 10% isn't a big deal. Okay, John, when you're answering questions, think about it before you just spurt out an answer, okay? We've been previously talking about when you have a 10% error, which is the example for the virus vaccine, that means 10% is ineffective, or there can be side effects. You don't want to take a chance on 10%. All right? So I want everybody, when you start hearing about studies or you're in a class and somebody talks about a study, this is not to be a pest or not to be irritating, but you could certainly ask, what was the standard error? What was the error that was used in this study? Okay? Because then you can turn around and look at it and go, well, a 10% standard error, that's not very good. There's going to be some flaws in this results, and you can get false positives or false negatives. That's what this is what I want people to understand this. Okay. Does anyone not understand about your desired level of confidence? Usually in statistics, you start at 95%. You do not do anything at 90%. Unless, and this is like an exception, is when it's the first time you're doing something. That's referred to as a beta test. You're not doing anything, that's going to affect anybody, as they said about the virus at, it's at 90%. Okay, I just want people to understand that. All right. So for a 95% confidence interval, about 95% of the similarly constructed intervals will contain the parameter being estimated. Also, 95% of the sample means for a specified sample size will lie within 1.96 standard deviations of the hypothesis population. Okay? This is the area where the little finger is. It's not grayed out. Okay? That is the 95% confidence interval. Okay? Mu, that's the mean. Okay? 1.96 is the standard deviation. Okay. So sample 1 of size 256, it includes the population mean. That's this line going across here. Okay. Sample 2 of size 256, it includes the population mean. So you see it's crossing over the mean here. So sample 3, it includes the population mean. Even though it's on, I'm looking from the front, the left side of the curve, that's X3. Sample 4, it includes the population mean. Sample 5, it does not include the population mean. So this is sample 5. Okay, it is on the right side, looking forward of the curve. And sample 6, size 256, includes the population mean. Okay, so you can see that you can take samples that cross over, but not necessarily represent this kind of curve. Okay, even though it is capturing the mean, but it's more here on the left side than the right side, and this is way more on the left side than the right side, and this is more on the right side than the left side. Okay, so I want to show a video on interpreting interval estimates.
We are told that a zookeeper took a random sample of 30 days and observed how much food an elephant ate on each of those days. The sample mean was 350 kilograms, and the sample standard deviation was 25 kilograms. The resulting 90% confidence interval for the mean amount of food was
from 341 kilograms to 359 kilograms. Which of the following statements is a correct interpretation of the 90% confidence level? Like always, pause this video and see if you can answer this on your own. So before we even look at these choices, let's just make sure we're reading the statement or interpreting the statement correctly. A zookeeper is trying.
Okay, this is also very important, and this is what I want people to pay attention to. Read the problem so you know exactly what information is being given and what information is being asked, and make sure that you understand exactly what the problem is and understand what the numbers are related to. It is also very important when you're given information like this, and think about it, if you're working for a company, you're not going to lay it out like this. You're going to have to figure it out yourself. Okay, so you want to pay attention to the given information as well as what the unknown is.
Trying to figure out what the true expected amount of food an elephant would eat on a day. You could view that as the mean amount of food that an elephant would eat on a day. If you view as the number, all the possible days as the population, you could view this as the population mean amount of food per day. Now the zookeeper doesn't know that. And so instead, they're trying to estimate it by sampling 30 days. Let's think about it this way. So let's say that this is the true population mean, the true mean amount of food that an elephant will eat in a day. What the zookeeper can try to do is, well, they take a sample, and in this case, they took a sample of 30 days, and they calculated a sample statistic, in this case, the sample mean, of 350 kilograms. I don't know if it's actually to the right of the true parameter, but just for visualization purposes, let's say it is. Let's say sample mean, and this is their first sample, it was 350 kilograms. And then using the sample, they were able to construct a confidence interval from 341 to 359 kilograms. So the confidence interval, I'll draw it like this. We actually aren't sure if it actually overlaps with the true mean, like I'm drawing here. Just for the sake of visualization purposes, let's say that this one happened to. The whole point of a 90% confidence level is if I kept doing this. So this is our first sample and the associated interval with that first sample. And then if I did another sample, let's say this is the mean of that next sample, so that's sample mean 2, and I have an associated confidence interval. And that interval, not only the start and end points will change, but the actual width of the interval might change depending on what my sample looks like. But a 90% confidence level means that if I keep doing this, 90% of my confidence intervals should overlap with the true parameter, with the true population mean. So now, with that out of the way, let's see which of these choices are consistent with that interpretation. So we say the elephant ate between 341 kilograms and 359 kilograms on 90% of all of the days. No, that is definitely not what is going on here. We're not talking about what's happening on 90% of the days. So let's rule this choice out. There is a...
Okay, I just want, does everybody understand why that is not true? Okay, everybody understands that? Okay.
0.9 probability that the true mean amount of food is between 341 kilograms and 359 kilograms. So this one is interesting. It is a tempting choice because when we do this one sample, you can kind of say, all right, if I did a bunch of these samples, 90% of them, if we have a 90% confidence interval, or 90% confidence level, should overlap with this true mean, with the population parameter. The reason why this is a little bit uncomfortable is it makes the true mean sound almost like a random variable, that it could kind of jump around, and it's the true mean that kind of is either going to jump into this interval or not jump into this interval. So it causes a little bit of unease. The choice, so I'm just going to put a question mark here. In repeated sampling, okay, I like the way that this is starting. In repeated sampling, this method produces intervals. Yep, that's what it does. Every time you sample, you produce an interval. that capture the population mean in about 90% of samples. Yeah, that's exactly what we're talking about. If we just kept doing this if we have well-constructed 90% confidence intervals, that if we kept doing this, 90% of these constructed sampled intervals should overlap with the true mean. So I like this choice. But let's just read choice D to rule it out. In repeated sampling, this method produces a sample mean between 341 kilograms and 359 kilograms in about 90% of samples. No, the confidence interval does not put a constraint on 90% of the time you will have a sample mean between these values. It is not trying to do that. It is definitely choice C.
Whoop. Okay. So from that example, basically what I want to show everybody is that you must read the question carefully, okay, and understand what it's saying to you so you can interpret it appropriately, because you can get confused by the language. And please, if you are confused, you'll have your textbook with you, you'll have whatever other source you have with you. Read the question carefully, okay? Okay. All right. So I don't know whether people have been using, or when you're, well, not using it very much, but how to obtain a Z value for a given confidence interval. So the 95% confidence refers to the middle 95% of the observations. Middle, the part that's not grayed, okay? And remember, this is symmetrical. It's a bell curve. 47.5% on one side, 47.5% on the other side. And because you're looking at 95%, the remaining percent are equally divided between the two tails. So if you get a Z score of 1.9, all right, and you're looking at 0.06 confidence level, there's the 47.50. There you go. All right. My suggestion is, when you're looking at examples in the chapter, try a little bit and look at the Z tables. There is a Z table, if people haven't printed it out yet, that I made available. Yes, there's a way to find the confidence intervals. I won't look at that right now. Okay, so I want you to look at that when you're looking at the tables, and quickly, we've got a video that we can look at here on internet. Oh, sorry, that's not the correct one. That's a T-score. I'm not sure why that. Just hold on a second and let me get to. Sorry about that. I don't know why I don't have the correct video. I've got the T distribution and the Z distribution. I apologize. Oh dear.
Let's look at finding the appropriate Z.
Okay, sorry about that. Not sure why I didn't have that. Anyways, We're going to look at the Z scores and how to find them.
Value using the standard normal table and constructing a confidence interval. Suppose we wish to use this confidence interval formula to obtain a 1 minus alpha times 100% confidence interval for mu. This would be the appropriate formula if we were sampling from a normally distributed population, where the population standard deviation sigma is known. And the subject of this video is how to find this Z sub alpha over 2 value using the standard normal table. The Z value is based on the standard normal distribution, and I've plotted in the standard normal distribution here. And if we want the confidence level to be 1 minus alpha times 100%, we put an area of 1 minus alpha in the middle of the distribution. The part that's left over is alpha, because the area under the entire distribution is 1. And we split this alpha evenly into the two tails, putting alpha over 2 in the right tail and alpha over 2 in the left tail. Z sub alpha over 2 is the Z value that has an area to the right of alpha over 2. Let's look at a specific example. What is the appropriate Z value for a 95% confidence interval? Well, here we're saying that 1 minus alpha times 100% is 95%. We put 95% of the area, 0.95, in the middle here.
Okay, so the first part, is anybody not clear on this formula? 1 minus alpha times 100% equals 95%. That's your confidence interval. So what is the alpha going to be here? Anybody? If 1 minus alpha times 100% equals 95%, what is this going to be? If you know that 1 minus alpha gives you 95%, what is alpha? What's 100 minus something gives you 95%? Five what, Song? Five what? %. Yeah. Okay, remember that.
This area is going to be 0.95. Alpha is the remaining area, 0.05. And we split that evenly into the two tails, putting an area of 0.025 in the right tail and an area of 0.025 in the left tail.
Okay, again, that's important. So remember, so this is the 95% in the middle here. We have alpha is 5%. Because this is a normal population, we split it where the 0 is. And this portion outside of our 95%, you have to split 0.05, divide by 2. You get 0.025 on the right side and 0.025 on the left side. Does anybody not see that? Okay? Because this is a standard normal curve, you've got to split when you're finding that. Okay?
Now we need to find this value that has an area to the right of 0.025 under the standard normal curve.
Okay. Now why are we looking at the right side here of the curve? Can anybody answer that question? Why are we only looking at this side? Nobody? what's the percentage left here? Okay. We'll continue.
We have to remember that the standard normal table that I use gives the area to the left. So the table gives the area to the left. And so when we go to the table, we're going to have to recognize that we need to look up the area to the left. And the area to the left of the value we need is 0.975. So let's go to the table and find that value. Here's my standard normal table, which gives areas to the left. And we need this area to be 0.975. Areas are found in the body of the table here, so we're going to have to look in here and get as close as we can to 0.975. And right here, we find 0.9750.
Okay, so when you're looking at your table, this is where you're 975, and that's why you're looking only on one side of the curve, because you're looking at what's greater than in the curve, because on the other side is negative values. Okay, not negative, but remember it adds up to 1, it would be 0.025. Okay, so when we look up the value, we find the 0.9750 value.
And so we go to the edges of the table to find 1.96. And so the appropriate Z value is 1.96.
Okay, so when you're looking at the table, on the left side, you will see a Z value. Okay. We know that 0.975, Z is equal to 1.96, so we see the 1.9 over here. We have to move across the table, 1.96, and we get 0.9750.
And so the table tells me that this value right here is 1.96. Or in other words, Z sub 0.025, the Z value with an area of 0.025 to the right is 1.96. This value over here, due to symmetry about 0, is minus 1.96.
Okay. 1.96 is 1.96 standard deviations from 0. Okay? We can look at that. And we know it's at the 95% confidence interval.
And so our confidence interval will be found by taking the value of the sample mean and adding and subtracting 1.96 times sigma over the square root of n. What is the appropriate Z value for a 75% confidence interval? Well, here we're going to put a middle area of 0.75. And alpha, the remaining bit, is 0.25. And alpha over 2 is 0.125. And so we're going to put this area of alpha over 2 in each of the tails, 0.125 and 0.125. And now we need to find this value. Well, this value has an area to the right of 0.125 and an area to the left of 0.875. Let's go to the table. We want to find the Z value that has an area to the left of 0.875. And so we look in the body of the table and get as close as we can to 0.875, and that's 0.8749 right here. And so we go to the edges to get our Z value, 1.15. And so the Z value that we need is approximately 1.15. So the table tells me that this value, the 2 decimal places, is 1.15. This value, by symmetry about 0, is minus 1.15. And so our Z sub 0.125 is approximately 1.15. And the appropriate 75% confidence interval is going to be x bar plus and minus 1.15 times sigma over the square root of n.
Okay. So I would like people to look at the text and try a few examples so you get used to looking at the table. Okay. And I'm going to go back to the PowerPoint. If you look at it carefully and do it step by step, it's very easy. Okay. All right. So point estimates and confidence intervals for a mean where the sigma is known. Okay. The x, sorry, this should be a x bar. Sorry, that's the sample mean. Z, the Z value for a particular confidence level. Sigma is the population standard deviation, and n is the number of observations in the sample. The width of the interval is determined by the level of confidence and the size of the standard error of the mean. The standard error is affected by two values, the standard deviation and the number of observations in the sample. So our example, the American Management Association wishes to have information on the mean income of middle managers in the retail industry. A random sample of 256 managers reveals a sample mean of $45,420. The standard deviation of this population is 2,050. The association would like answers to the following questions. What is the population mean? In this case, we do not know, right? But we know what the sample mean is. We do know the sample mean is 45,420. Hence, our best estimate of the unknown population value is the corresponding sample statistic. What is the reasonable range of values for the population mean? Use, and this will always be in the questions, use 95% confidence level. Here's the formula. So we have 45, this is determining the confidence level. 45,420 plus or minus 1.96, okay, multiplied by 2,050, the standard deviation, divided by the square root of 256, that's your n, okay? And remember, this is the 95% confidence interval. We have 45,420 plus or minus $251. So the confidence limit are 45,169 at one end and 45,671 at the other end, adding and subtracting $251 from 45,420. So the plus minus 251 is referred to as the margin of error. And what do the results mean? And this is where I want you to write down the answers in sentences. Okay, you can do all your calculations and that's fine. This becomes important as part of your solution to the questions and gets marked as well. So if we select many samples of 256 managers, and for each sample we compute the mean and then construct 95% confidence interval, we could expect about 95% of these confidence intervals to contain the population mean. Okay? Because you're saying, remember, this is 256 as your sample. It's over 30. So this mean approximates the population. So we can say about 95% contain the population mean, which is 45,420. If we look at this range between 45,169 and 45,671. All right, does anybody have any questions about that example? There are no questions. Okay, does anybody have any questions about what we've done so far in Chapter 8? No questions. Okay. So as I remind you, the Chapter 7 test, I'll send out a note again, will be available on Friday. And I will send out a note regarding what the homework is for Chapter 7. And so thank you very much, everybody. And remember, if you have any questions or concerns, office hours tomorrow from 10 to 12. All right. So everybody have a good evening and enjoy the weather. Thank you.